Onboard diagnostics is an automotive term referring to a vehicle's self-diagnostic and reporting capability. OBD systems give the vehicle owner or repair technician access to the status of the various vehicle subsystems. The amount of diagnostic information available via OBD has varied widely since its introduction in the early 1980s versions of onboard vehicle computers. Early versions of OBD would simply illuminate a malfunction indicator light or idiot light if a problem was detected but would not provide any information as to the nature of the problem. Modern OBD implementations use a standardized digital communications port to provide real-time data in addition to a standardized series of diagnostic trouble codes, or DTCs, which allow one to rapidly identify and remedy malfunctions within the vehicle. History: 1969, Volkswagen introduces the first onboard computer system with scanning capability, in their fuel-injected Type 3 models. 1975, Datsun 280Z onboard computers begin appearing on consumer vehicles, largely motivated by their need for real-time tuning of fuel injection systems. Simple OBD implementations appear, though there is no standardization in what is monitored or how it is reported. 1980, General Motors implements a proprietary interface and protocol for testing of the engine control module on the vehicle assembly line. The assembly line diagnostic link protocol communicates at 160 baud with pulse width modulation signaling and monitors very few vehicle systems. Implemented on California vehicles for the 1980 model year, and the rest of the United States in 1981, the ALDL was not intended for use outside the factory. The only available function for the owner is blinky codes. The diagnostic trouble codes can be interpreted through the blinking pattern of the check engine light. 1986, an upgraded version of the ALDL protocol appears which communicates at 8192 baud with half-duplex UART signaling. This protocol is defined in GMX DE 5024B, 1988. The Society of Automotive Engineers recommends a standardized diagnostic connector and set of diagnostic test signals. 1991, the California Air Resources Board requires that all new vehicles sold in California in 1991 and newer vehicles have some basic OBD capability. These requirements are generally referred to as OBDI, though this name is not applied until the introduction of OBDE. The data link connector and its position are not standardized, nor is the data protocol. 1994, motivated by a desire for a statewide emissions testing program, the CARB issues the OBDII specification and mandates that it be adopted for all cars sold in California starting in model year 1996. The DTCs and connector suggested by the SA are incorporated into this specification. 1996, the OBDII specification is made mandatory for all cars sold in the United States. 2001, the European Union makes the OBD mandatory for all gasoline vehicles sold in the European Union, starting in MY 2001. 2003, the European Union makes the OBD mandatory for all diesel vehicles sold in the European Union. 2008. All cars sold in the United States are required to use the ISO 15765-4 signaling standard bus. 2008, certain light vehicles in China are required by the Environmental Protection Administration Office to implement OBD by July 1, 2008. Some regional exemptions may apply. 2010, HD OBD specification is made mandatory for selected commercial engines sold in the United States. Standard Interfaces, ALDL. GM's ALDL is sometimes referred as a predecessor to, or a manufacturer's proprietary version of, an OBDI diagnostic. This interface was made in different varieties and changed with powertrain control modules. Different versions had slight differences in pinouts and baud rates. Earlier versions used a 160 baud rate, while later versions went up to 8192 baud and used bidirectional communications to the PCM. OBDI. The regulatory intent of OBDI was to encourage auto manufacturers to design reliable emission control systems that remain effective for the vehicle's useful life. The hope was that by forcing annual emissions testing for California, and denying registration to vehicles that did not pass, drivers would tend to purchase vehicles that would more reliably pass the test. OBDI was largely unsuccessful, as the means of reporting emission-specific diagnostic information was not standardized. Technical difficulties with obtaining standardized and reliable emissions information from all vehicles led to an inability to implement the annual testing program effectively. The diagnostic trouble codes of OBDI vehicles can usually be found without an expensive scan tool. Each manufacturer used their own diagnostic link connector, DLC location, DTC definitions, and procedure to read the DTCs from the vehicle. DTCs from OBDI cars are often read through the blinking patterns of the check engine light or service engine zoom light. By connecting certain pins of the diagnostic connector, the check engine light will blink out a 2-digit number that corresponds to a specific error condition. The DTCs of some OBDI cars are interpreted in different ways, however. Cadillac fuel-injected vehicles are equipped with actual onboard diagnostics, providing trouble codes, actuator tests and sensor data through the new digital electronic climate control display. Holding down off and warmer for several seconds activates the diagnostic mode without the need for an external scan tool. Some Honda engine computers are equipped with LEDs that light up in a specific pattern to indicate the DTC. General Motors, some 1989 to 1995 Ford vehicles, and some 1989 to 1995 Toyota Lexus vehicles have a live sensor data stream available, however, many other OBDI-equipped vehicles do not. OBDI vehicles have fewer DTCs available than for OBDI-equipped vehicles. OBD 1.5 OBD 1.5 refers to a partial implementation of OBDI which General Motors used on some vehicles in 1994, 1995, and 1996. For example, the 94 Euro 95 Corvettes have one post-catalyst oxygen sensor, and have a subset of the OBDI codes implemented. For a 1994 Corvette the implemented OBDI codes are P0116, P0118. P0131, P0135, P0151, P0155, P0158, P0160, P0161, P0171, P0175, P0420, P1114, P1115, P1133, P1153 and P1158. This hybrid system was present on the GMH body cars in 94 to 95, W body cars, Chevrolet Monte Carlo, Pontiac Grand Prix, Oldsmobile Cutlass Supreme, in 94 to 95, L body in 94 to 95, Y body in 94 to 95, on the F body in 95 and on the J body and N body in 95 and 96 and also on 94-95 Saab vehicles with the naturally aspirated 2.3. The pinout for the ALDL connection on these cars is as follows. For ALDL connections, pin 9 is the data stream, pins 4 and 5 are ground, and pin 16 is battery voltage. An OBD 1.5 compatible scan tool is required to read codes generated by OBD 1.5. Additional vehicle-specific diagnostic and control circuits are also available on this connector. For instance, on the Corvette there are interfaces for the Class 2 serial data stream from the PCM, the CCM diagnostic terminal, the radio data stream, the airbag system, the selective ride control system, the low tire pressure warning system, and the passive keyless entry system. An OBD 1.5 has also been used on Mitsubishi cars of 95-97 vintage, some 1995 Volkswagen VR6s, Buick Riviera of 1995 vintage and in the Ford Scorpio since 95. OBDI is an improvement over OBDI in both capability and standardization. The OBDI standard specifies the type of diagnostic connector and its pinout, the electrical signaling protocols available, and the messaging format. It also provides a candidate list of vehicle parameters to monitor along with how to encode the data for each. There is a pin in the connector that provides power for the scan tool from the vehicle battery, which eliminates the need to connect a scan tool to a power source separately. However, some technicians might still connect the scan tool to an auxiliary power source to protect data in the unusual event that a vehicle experiences a loss of electrical power due to a malfunction. Finally, the OBDII standard provides an extensible list of DTCs. As a result of this standardization, a single device can query the onboard computer in any vehicle. This OBDII came in two models, OBDII-A and OBDII-B. OBDII standardization was prompted by emissions requirements, and though only emission-related codes and data are required to be transmitted through it, most manufacturers have made the OBDII data link connector the only one in the vehicle through which all systems are diagnosed and programmed. OBDII diagnostic trouble codes are 4-digit, preceded by a letter, P for engine and transmission, B for body, C for chassis, and U for network. OBDII diagnostic connector. The OBDII specification provides for a standardized hardware interface the female 16-pin J1962 connector. Unlike the OBDII connector, which was sometimes found under the hood of the vehicle, the OBDII connector is required to be within 2 feet of the steering wheel. SAJ 1962 defines the pin out of the connector as, the assignment of unspecified pins is left to the vehicle manufacturer's discretion. EOBD, the EOBD regulations are the European equivalent of OBDII, and apply to all passenger cars of category M1 first registered within EU member states since January 1, 2001 for petrol-engined cars and since January 1, 2004 for diesel-engined cars. For newly introduced models, the regulation dates applied a year earlier, January 1, 2000 for petrol and January 1, 2003 for diesel. For passenger cars with a gross vehicle weight rating of greater than 2,500 kg and for light commercial vehicles, the regulation dates applied from January 1, 2002 for petrol models, and January 1, 2007 for diesel models. The technical implementation of the OBD is essentially the same as OBDII, with the same SAJ 1962 diagnostic link connector and signal protocols being used. With Euro V and Euro 6 emission standards, EOBD emission thresholds will be lower than previous Euro 3 and 4 EOBD fault codes. Each of the EOBD fault codes consists of 5 characters, a letter, followed by 4 numbers. The letter refers to the system being interrogated, for example PXXXX would refer to the powertrain system. The next character would be a 0 if complies to the EOBD standard. So it should look like POXXX. The next character would refer to the subsystem. POOXX, fuel and air metering and auxiliary emission controls, PO1XX, fuel and air metering, PO2XX, fuel and air metering, PO3XX, ignition system or misfire, PO4XX, auxiliary emissions controls, PO5XX, vehicle speed controls and idle control system, PO6XX, computer output circuit, PO7XX, transmission, PO8XX, transmission. The following 2 characters would refer to the individual fault within each subsystem. EOBD2, the term EOBD2 is marketing speak used by some vehicle manufacturers to refer to manufacturer-specific features that are not actually part of the OBD or EOBD standard. In this case E stands for enhanced. JOBD is a version of OBDII for vehicles sold in Japan. ADR 79/01 and 79/02, the ADR 79/01 2005, standard is the Australian equivalent of OBDE. It applies to all vehicles of category M1 and N1 with a gross vehicle weight rating of 3,500 kg or less, registered from new within Australia and produced since January 1, 2006 for petrol-engined cars and since January 1, 2007 for diesel-engined cars. For newly introduced models, the regulation dates applied a year earlier, January 1, 2005 for petrol and January 1, 2006 for diesel. The ADR 79/01 standard was supplemented by the ADR 79/02 standard which imposed tighter emissions restrictions, applicable to all vehicles of Class M1 and N1 with a gross vehicle weight rating of 3,500 kg or less, from July 1, 2008 for new models, July 1, 2010 for all models. The technical implementation of this standard is essentially the same as OBDII, with the same SAJ 1962 diagnostic link connector and signal protocols being used. OBDII signal protocols. There are 5 signaling protocols that are permitted with the OBDII interface. Most vehicles implement only one of the protocols. It is often possible to deduce the protocol used based on which pins are present on the J1962 connector, SAEJ 1850PWM, pin 2, bus plus, pin 10, bus a euro, high voltage is plus 5 V, message length is restricted to 12 bytes, including CRC, employs a multi-master arbitration scheme called carrier sense multiple access with non-destructive arbitration. SAEJ 1850 VPW, pin 2, bus plus, bus idles low, high voltage is plus 7 V, decision point is plus 3.5 V, message length is restricted to 12 bytes, including CRC, employs CSMANDA. ISO 9141-2. This protocol has an asynchronous serial data rate of 10.4 K baud. It is somewhat similar to RS-232. However, the signal levels are different, and communications happens on a single, bidirectional line without additional handshake signals. ISO 9141-2 is primarily used in Chrysler, European, and Asian vehicles, pin 7, K-line, pin 15, L-line, UART signaling. K-line idles high, with a 510 ohm resistor to VBATT, the active dominant state is driven low with an open collector driver. Message length is max 260 bytes. Data field max 255. ISO 14230 kWp 2000, pin 7, K-line, pin 15, L-line, physical layer identical to ISO 9141-2, data rate 1.2 to 10.4 K baud, message may contain up to 255 bytes in the data field. ISO 15765 CAN. The CAN protocol was developed by Bosch for automotive and industrial control. Unlike other OBD protocols, variants are widely used outside of the automotive industry. While it did not meet the OBDII requirements for U.S. vehicles prior to 2003, as of 2008 all vehicles sold in the U.S. are required to implement CAN as one of their signaling protocols. Pin 6, CAN high, pin 14, CAN low. All OBDII pinouts use the same connector, but different pins are used with the exception of pin 4 and pin 16. OBDII diagnostic data available. OBDII provides access to data from the engine control unit and offers a valuable source of information when troubleshooting problems inside a vehicle. The SAJ 1979 standard defines a method for requesting various diagnostic data and a list of standard parameters that might be available from the ECU. The various parameters that are available are addressed by parameter identification numbers, or PIDs, which are defined in J 1979. For a list of basic PIDs, their definitions, and the formula to convert raw OBDII output to meaningful diagnostic units, see OBDIE PIDs. Manufacturers are not required to implement all PIDs listed in J 1979 and they are allowed to include proprietary PIDs that are not listed. The PID request and data retrieval system gives access to real-time performance data as well as flagged DTCs. For a list of generic OBDIE DTCs suggested by the SAE, see Table of OBDII codes. Individual manufacturers often enhance the OBDII code set with additional proprietary DTCs. Mode of operation. Here is a basic introduction to the OBD communication protocol according to ISO 15031. Mode $1 is used to identify what powertrain information is available to the scan tool. Mode $2 displays freeze frame data. Mode $3 lists the emission-related confirmed diagnostic trouble codes stored. It displays exact numeric, 4-digit codes identifying the faults. Mode $4 is used to clear emission-related diagnostic information. This includes clearing the stored pending confirmed DTCs and freeze frame data. Mode $5 displays the oxygen sensor monitor screen and the test results gathered about the oxygen sensor. There are 10 numbers available for diagnostics: $1 rich to lean O2 sensor threshold voltage, $2 lean to rich O2 sensor threshold voltage, $3 low sensor voltage threshold for switch time measurement, $4 high sensor voltage threshold for switch time measurement, $5 rich to lean switch time and miss, $6 lean to rich switch time and miss, $7 minimum voltage for test, $8 maximum voltage for test, $9 time between voltage transitions and miss. Mode $6 is a request for onboard monitoring test results for continuously and non-continuously monitored system. There are typically a minimum value, a maximum value, and a current value for each non-continuous monitor. Mode $7 is a request for emission-related diagnostic trouble codes detected during current or last completed driving cycle. It enables the external test equipment to obtain pending diagnostic trouble codes detected during current or last completed driving cycle for emission-related component systems. This is used by service technicians after a vehicle repair, and after clearing diagnostic information to see test results after a single driving cycle to determine if the repair has fixed the problem. Mode $8 could enable the off-board test device to control the operation of an onboard system, test, or component. Mode $9 is used to retrieve vehicle information. Among others, the following information is available: van vehicle ID, CALID, ID for the software installed on the ECU, CVN, number used to verify the integrity of the vehicle software. The manufacturer is responsible for determining the method of calculating CVN, for example using checksum. In-use performance counters, gasoline engine e-catalyst, primary oxygen sensor, evaporating system, EGR system, VVT system, secondary air system, and secondary oxygen sensor, diesel engine ENMHC catalyst, NOx reduction catalyst, NOx absorber particulate matter filter, exhaust gas sensor, EGR system, VVT system, boost pressure control, fuel system. Mode $0 lists emission-related permanent diagnostic trouble codes stored. As per CARB, any diagnostic trouble codes that is commanding MIL on and stored into non-volatile memory shall be logged as a permanent fault code. Obd Applications. Various tools are available that plug into the OBD connector to access OBD functions. These range from simple generic consumer-level tools to highly sophisticated OEM dealership tools to vehicle telematic devices. Handheld scan tools. A range of rugged handheld scan tools is available. Simple fault code readers reset tools are mostly aimed at the consumer level. Professional handheld scan tools may possess more advanced functions, access more advanced diagnostics, set manufacturer or vehicle-specific ECU parameters, access and control other control units, such as airbag or ABS, real-time monitoring or graphing of engine parameters to facilitate diagnosis or tuning. Mobile device-based tools and analysis. Mobile device applications allow mobile devices such as cell phones and tablets to display and manipulate the OBD-II data accessed via USB adapter cables or Bluetooth adapters plugged into the car's OBD2 connector. PC-based scan tools and analysis platforms. A PC-based OBD analysis tool that converts the OBD-II signals to serial data standard to PCs or Macs. The software then decodes the received data to a visual display. Many popular interfaces are based on the ELM or STN1110 OBD interpreter ICs, both of which read all 5 generic OBD-II protocols. Some adapters now use the J2534 API, allowing them to access OBD-II protocols for both cars and trucks. In addition to the functions of a handheld scan tool, the PC-based tools generally offer large storage capacity for data logging and other functions, higher resolution screen than handheld tools, the ability to use multiple software programs adding flexibility, the extent that a PC tool may access manufacturer or vehicle-specific ECU diagnostics varies between software products as it does between handheld scanners. Data loggers. Data loggers are designed to capture vehicle data while the vehicle is in normal operation, for later analysis. Data logging uses include engine and vehicle monitoring under normal operation, for the purpose of diagnosis or tuning. Some U.S. auto insurance companies offer reduced premiums if OBDII vehicle data loggers or cameras are installed, and if the driver's behavior meets requirements. This is a form of auto insurance risk selection, monitoring of driver behavior by fleet vehicle operators. Analysis of vehicle black box data may be performed on a periodic basis, automatically transmitted wirelessly to a third party or retrieved for forensic analysis after an event such as an accident, traffic infringement or mechanical fault. Emission testing. In the United States, many states now use OBDII testing instead of tailpipe testing in OBDII-compliant vehicles. Since OBDII stores trouble codes for emissions equipment, the testing computer can query the vehicle's onboard computer and verify there are no emission-related trouble codes and that the vehicle is in compliance with emission standards for the model year it was manufactured. In the Netherlands, 2006 and later vehicles get a yearly EOBD emission check. Driver's supplementary vehicle instrumentation. Driver's supplementary vehicle instrumentation is instrumentation installed in a vehicle in addition to that provided by the vehicle manufacturer and intended for display to the driver during normal operation. This is opposed to scanners used primarily for active fault diagnosis, tuning, or hidden data logging. Auto enthusiasts have traditionally installed additional gauges such as manifold vacuum, battery current etc. The OBD standard interface has enabled a new generation of enthusiast instrumentation accessing the full range of vehicle data used for diagnostics, and derived data such as instantaneous fuel economy. Instrumentation may take the form of dedicated trip computers, computer or interfaces to PDAs, smartphones, or a Garmin navigation unit. As a computer is essentially a PC, the same software could be loaded as for PC-based scan tools and vice versa, so the distinction is only in the reason for use of the software. These enthusiast systems may also include some functionality similar to the other scan tools. Vehicle telematics. OBD2 is no longer only used by professionals and hobbyists to repair vehicles. OBD2 information is commonly used by vehicle telematics devices that perform fleet tracking, monitor fuel efficiency, prevent unsafe driving, as well as for remote diagnostics and buy pay-as-you-drive insurance. Although originally not intended for the above purposes, commonly supported OBD2 data such as vehicle speed, RPM, and fuel level allow GPS-based fleet tracking devices to monitor vehicle idling times, speeding, and over-revving. By monitoring OBD2 DTCs, a company can know immediately if one of its vehicles has an engine problem and by interpreting the code the nature of the problem. OBD2 is also monitored to block mobile phones when driving and to record trip data for insurance purposes. Standards documents. SAE standards documents on OBDE, J 1962, defines the physical connector used for the OBDII interface. J 1850, defines a serial data protocol. There are two variants, 10.4 kbits and 41.6 kbits. Mainly used by U.S. manufacturers, also known as PCI, Class II, and SCP, J 1978, defines minimal operating standards for OBDII scan tools. J 1979, defines standards for diagnostic test modes. J 2012, defines standards, trouble codes and definitions. J 2178-1, defines standards for network message header formats and physical address assignments. J 2178-2, gives data parameter definitions. J 2178-3, defines standards for network message frame IDs for single byte headers. J 2178-4, defines standards for network messages with 3-byte headers. J 2284-3, defines 500K CAN physical and data link layer. J 2411, describes the GMLAN protocol, used in newer GM vehicles. Often accessible on the OBD connector as pin 1 on newer GM vehicles. SAE standards documents on HD OBD, J 1939, defines a data protocol for heavy-duty commercial vehicles, ISO standards, ISO 9141, road vehicles diagnostic systems. International Organization for Standardization, 1989. Part 1, Requirements for Interchange of Digital Information, Part 2, CARB Requirements for Interchange of Digital Information, Part 3, Verification of the communication between vehicle and OBD2 scan tool. ISO 11898, Road Vehicles Controller Area Network. International Organization for Standardization, 2003. Part 1, Data Link Layer and Physical Signaling, Part 2, High-Speed Medium Access Unit, Part 3, Low-Speed, Fault-Tolerant, Medium-Dependent Interface, Part 4, Time-Triggered Communication. ISO 14230, Road Vehicles Diagnostic Systems Keyword Protocol 2000, International Organization for Standardization, 1999. Part 1, Physical Layer, Part 2, Data Link Layer, Part 3, Application Layer, Part 4, Requirements for Emission-Related Systems. ISO 14320 No Data, ISO 15031, Communication between vehicle and external equipment for emissions-related diagnostics, International Organization for Standardization, 2010. Part 1, General Information and Use Case Definition, Part 2, Guidance on Terms, Definitions, Abbreviations and Acronyms, Part 3, Diagnostic Connector and Related Electrical Circuits, Specification and Use, Part 4, External Test Equipment, Part 5, Emissions-Related Diagnostic Services, Part 6, Diagnostic Trouble Code Definitions, Part 7, Data Link Security. ISO 15765, Road Vehicles Diagnostics on Controller Area Networks. International Organization for Standardization, 2004. Part 1, General Information, Part 2, Network Layer Services ISO 15765-2, Part 3, Implementation of Unified Diagnostic Services, Part 4, Requirements for Emissions-Related Systems. Security Issues. Researchers at the University of Washington and University of California examined the security around OBD, and found that they were able to gain control over many vehicle components via the interface. Furthermore, they were able to upload new firmware into the engine control units. Their conclusion is that vehicle embedded systems are not designed with security in mind. There have been reports of thieves using specialist OBD reprogramming devices to enable them to steal cars without the use of a key. The primary causes of this vulnerability lie in the tendency for vehicle manufacturers to extend the bus for purposes other than those for which it was designed, and the lack of authentication and authorization in the OBD specifications, which instead rely largely on security through obscurity. See also, OBD EPIDs, Engine Control Unit, Immobilizer. References. Notes. External links. OBDII codes definition. OBDII codes definition, description and repair information for most makes of vehicles. 1. Directive 98/EC of the European Parliament and of the Council of October 13, 1998. National OBD Clearinghouse Center for Automotive Science and Technology at Weber State University, OBDII codes definition. OBDII codes definition, description and repair information. United States Environmental Protection Agency OBD information for repair technicians, vehicle owners, and manufacturers, OBD2 vehicle plug pinouts including compatibility lists, manufacturer-specific OBDII diagnostics pinouts and compatibility information.